Sum of products method. Sum of products method is a way of deriving a logic circuit from a truth table. Now we want to derive a logic circuit which produces a given truth table. For this, we will use sum of products method. First, we will see what are fundamental products. Following tables summarizes all possible ways to end two signals A and B and three signals A, B and C in complemented or uncomplemented form to get high output. This is table for two inputs A and B. When there are two inputs, we have these four combinations. 2 to the power 2, 4 combinations are possible, that are 0, 0, 0, 1, 1, 0 and 1, 1. Now we see what are fundamental product. Fundamental product for first combination in which A is 0 and B is 0 is A bar B bar. This fundamental product is such that it will produce high output. If A is 0, B is 0, then A bar is 1 and B bar is 1 and 1.1 is 1. So to produce high output for this combination 0, 0, we must use complemented form of A and B and their product, A bar dot B bar or simply A bar B bar. If we take second combination in which A is 0, B is 1, then fundamental product will be A bar B. Because A is 0, so A bar will be equal to 1 and B is already 1. So we have fundamental product A bar B. And similarly for the combination 1, 0, we have fundamental product A B bar. And for combination 1, 1, we have fundamental product AB. Similarly, we can find fundamental products for three inputs A, B and C. These fundamental products are shown in this table for three inputs A, B and C. When inputs are 3, then possible combinations are 2 to the power 3, that is equal to 8. So these 8 combinations are possible and corresponding fundamental products are shown in this table. So the fundamental products are AND, of 2 or 3 signals in complemented or uncomplemented form to get high output. Deriving a logic circuit. Now we will see how we can derive a logic circuit for a given truth table by using these fundamental products. Let us consider this truth table for three inputs A, B and C. Output Y is 1 in 4 combinations. So we write fundamental products for those output Y which are 1. First output Y is 1 when this is the combination 0, 1, 0. A is 0, B is 1, C is 0. For this combination, fundamental product will be A bar B C bar. B is 1 and A and C are 0, so we use A bar and C bar. Similarly, next output 1 will be for combination 1 0 1 and fundamental product for this is A B bar C, and for 1 1 0 fundamental product is A B C bar, and for 1 1 1 fundamental product is A B C. We write these fundamental products. We draw 6 lines, 3 for 3 inputs A, B and C, and 3 for their complements A bar, B bar and C bar. And because there are 4 output that are high, and we write 4 fundamental products for those. So we will use 4 AND gates. In one AND gate, the inputs must be A bar, B and C bar, which is one of the fundamental product. In second AND gate, we must have inputs as A, B bar and C, which is second fundamental product, and so on. And then output of these AND gates will be made input to OR gate, and output of this OR gate Y will be equal to sum of all these fundamental products. That is, Y will be equal to A bar B C bar plus A B bar C plus A B C bar plus A B C. And this logic circuit, which gives output Y by this equation, will produce this given truth table. So fundamental products can be used to drive a logic circuit to produce a given truth table. Now we want simplest logic circuit which gives the given truth table. To simplify, 2 methods are used. One is algebraic simplification and the other is Karnaugh maps. In algebraic simplification, after obtaining a sum of product equation, we have to simplify the circuit if possible. One way to do this is with Boolean algebra, and another way is by using Karnaugh maps. For example, if we have sum of product equation as y equal to a b bar plus ab, then we simplify it by using Boolean algebra. A b bar plus ab can be written as a into b bar plus b. A is common in both terms, and by using Boolean algebra, b bar plus b is equal to 1. So we have a into b bar plus b equal to a dot 1, and a dot 1 is equal to a. So this expression y equal to a b bar plus ab will be simplified to simply y equal to a. Logic circuit required for this first equation, y equal to a b bar plus ab, is this, which is shown in this figure A. And logic circuit for simplified expression y equal to a is shown in figure C. both logic circuits of figure A and figure C will produce the given truth table. So we have to use simplified expression so that a simplified logic circuit can be formed. If we have sum of product equation as y equal to a bar b bar c d plus a bar b c d plus a b bar c bar d, then we can simplify this equation as y equal to a bar c d into b bar plus b, a bar c d dot b bar plus b. A bar c d is common in first and second term, and remaining terms are b bar plus b. And b bar plus b is equal to 1. So we have y equal to a bar c d dot 1 plus a b bar c bar d, and a bar c d dot 1 is equal to a bar c d. So we have y equal to a bar c d plus a b bar c bar d. This is the simplified expression for output y, and using this simplified expression we can find a simplified logic circuit for a given truth table. Now we see what are Karnaugh maps. Sum of product equation can also be simplified by constructing Karnaugh maps. We want to find simplified logic circuit for a given truth table. So one way of simplification of logical expression was by using Boolean algebra, and other method is by using Karnaugh maps. So we will see what are Karnaugh maps, how they are constructed, and how they are used in simplifying logical expression and find a simplified logic circuit producing given truth table. First we consider two variable Karnaugh map. Consider a truth table with two variables a and b as shown in figure A. To construct Karnaugh map, first of all draw figure B. This is the truth table, any truth table for two variables, two inputs a and b. Output y is 1 for two combinations. Karnaugh map for two variables is constructed in this way. We draw a rectangle, write a bar and a in left side as a column, and b bar and b on upper side as a row. Now we see the fundamental products. Since output y is 1 for these two combinations 1 0 and 1 1, and fundamental products for these two combinations are a b bar and a b. So we put one for each of these two fundamental products. So we put 1 at two places which corresponds to fundamental product a b bar and a b. For a b bar we take row of a and column of b bar. And for second fundamental product, that is AB, we take row of A and column of B and put 1 there, and remaining 2 places we put 0 0. So in this way Karnaugh map is prepared for 2 inputs A and B. If we have 3 inputs A, B and C, we will use 3 variable map. This is the truth table, any given truth table for 3 variables A, B and C. Karnaugh map is constructed in this way. In left side, in form of column, we write A bar, B bar, A bar, B, A B, A B bar. Remember this order. We have to write in this order. A bar, B bar, A bar, B, A B, A B bar. And in the upper side, we write as a row as C bar C. Now we find the fundamental products for which output Y is 1. In this table, output Y is 1 for 3 combinations. First one is 0 1 0, for which fundamental product is A bar B C bar. So corresponding to this fundamental product A bar B C bar, we choose row of A bar B and column of C bar and put 1 according to this. Similarly, we put other 2 ones corresponding to other 2 fundamental products, and in remaining places we put 0. In this way, a 3 variable Karnaugh map is prepared. Similarly, we can construct 4 variable map. This is any given truth table for 4 inputs A, B, C and D. 4 variable Karnaugh map is constructed in this way. On left side, as a column, we write A bar, B bar, A bar, B, A B, A B bar, and on upper side as a row we write C bar, D bar, C bar, D, C D, C D bar. Remember this order. And again we find fundamental products corresponding these output Y equal to 1. Output Y is 1 for 4 combinations. So we have 4 fundamental products for this truth table, and corresponding to these 4 fundamental products we put ones in this Karnaugh map, and at all other places we put 0. And in this way Karnaugh map for a given truth table having 4 inputs A, B, C and D is prepared. Now we will see how we can make the simplification using Karnaugh map. Karnaugh simplification: to get simplified logic circuits from a given truth table, we first construct Karnaugh map and then look at pairs, quads and octets of ones. First look at pairs. If this is the Karnaugh map, we have a pair of ones which is encircled in this figure. In this figure we have 2 pairs of ones. Figure A contains a pair of ones which are encircled in figure B. These corresponds to products ABCD and ABCD bar. This is the figure B. We encircle a pair of ones. First one corresponds to fundamental product ABCD and second one corresponds to fundamental product ABCD bar. So logical expression for this truth table corresponding to this Karnaugh map shown in figure B is y equal to ABCD plus ABCD bar. ABC is common and we have ABC dot D plus D bar. D plus D bar is 1 and we get it equal to ABC into 1, that is ABC. Look at this figure B. By looking at this Karnaugh map, we can directly write this simplified expression. For this pair, on left hand side we have AB and in upper side we have for this pair two products CD and CD bar. So in these two products CD and CD bar, D change to D bar and C is same. So we take AB from left and we take C from upper side, which is not changed, and omitting the D and D bar because D changed to D bar. In this way we can find simplified logical expression y equal to ABC. By looking at this Karnaugh map, and which is true by this algebraic simplification, we also get y equal to ABC. In this way, if a pair is constructed, then we find a simplified logical expression by using Karnaugh map. If two pairs are formed as shown in this figure, for left side pair we will get y equal to A C bar D bar. C bar D bar is for both ones of this pair, and out of these AB and AB bar we take only A because B is changing to B bar. So from left hand side we get A and from upper side we get C bar D bar. So for left side pair we have A C bar D bar, and for next pair similarly we get A bar B D. From C bar D and CD we take D and ignore C bar and C because C bar changed to C. So for this Karnaugh map we will get output y equal to A C bar D bar plus A bar B D by simply looking at this Karnaugh map. Next is the quad. Combination of four ones like that is in this figure A or that as in this figure B. If there is such combinations of four ones, either these ones are in a row or in a column or in this form of a rectangle, we encircle them. This is a quad. Quad means 4. There are 4 ones in this order. If there are 4 ones and making a quad like that is in figure A, it can be assumed as 2 pairs as shown in figure C. For first pair we have expression y equal to ABC bar, and for second pair we have expression y equal to ABC. So we will get y equal to ABC bar plus ABC. AB is common, we have AB into C bar plus C. C bar plus C is 1. So we get y equal to AB. if we look at this quad, we can directly write this expression y equal to AB, because on left hand side for this quad we have AB, and on upper side first is C bar D bar, then it changes to C bar D, then it changes to CD, then it changes to CD bar. So these all are changed from complemented to uncomplemented or uncomplemented to complemented. So we ignore all these and write only y equal to AB for a quad. For a pair we have 3 bits, for a quad we have only 2 bits, y equal to AB. In this way, if we find a quad, the algebraic expression is very much simplified. And now the octet, if we have octet, combination of 8 ones as shown in this figure, this may be assumed as equal to these 2 quads. For first quad we have expression A C bar, A from left side and C bar from upper side, which do not change, and ignore the bits which changes. Similarly, for second quad we write y equal to A C. So for these 2 quads we have y equal to AC bar plus AC. Y equal to AC bar plus AC, A is common, that is A into C bar plus C, C bar plus C is 1, so A into 1, that is 1, that is A. So we get very simplified expression y equal to A. And if we look at this octet, we can directly write this expression y equal to A, because from left hand side we get A, B is changing to B bar, and from upper side all changes from complemented to uncomplemented or uncomplemented to complemented. So we have, by looking this Karnaugh map, we can write directly output y equal to A. So if we have octet, we have only 1 bit in expression for output y. If we have quad, we have 2 bits. If we have pair, we have 3 bits. In this way, a simplified logical expressions are obtained, and from which we can construct simplified logic circuits. Overlapping groups. When we encircle ones, we can use the same one more than once. The simplified equation for overlapping groups of following figure A is, this is figure in which a octet is formed, 8 ones, and a 1 remains. This remaining one can form a pair if we use one of this octet. We can overlap in this way, and for this octet we write y equal to A, and for this pair we write y equal to B C bar D. So output y for this Karnaugh map will become y equal to A plus B C bar D. Next is rolling the map. If we have 2 such pairs at 2 ends, we can consider it as a quad, because if we roll this, these 2 pairs come close together and form a quad. If it is it form a quad, then we can write a simplified expression y equal to b d bar, b from left side and d bar from upper side, because in upper side we have c bar d bar and c d bar. We take d bar from upper side and from left side we take b. So expression for output y for this Karnaugh map will be b d bar. Next is redundant groups. A group whose ones are all overlapped by other groups is called a redundant group. We must eliminate this group in writing the simplified Boolean equation. If we have this Karnaugh map, there are two pairs in left and right, and in the middle we also form a pair by overlapping. In this middle pair, both ones are included in other pairs. So this middle pair of ones is known as redundant groups, and we must ignore when we write a logical expression for this Karnaugh map. Now we consider an example. Write the simplified Boolean equation for the Karnaugh map of figure A and draw its logic circuit. This is the Karnaugh map. We have to draw logic circuit for this Karnaugh map. For this Karnaugh map, we first look at octet. There is no octet. Then we look at quads. There are three quads formed in this way by overlapping also, and then one remains which can make a pair by overlapping lower one. In this way we get three quads and one pair, and for these three quad and one pair we can write output y as equal to AB plus AC plus AD plus BCD. For this quad in which 1 1 1 1 are in a row, we write y equal to AB. For left hand side quad of remaining two quads, we write y equal to AD. For right side quad, we write y equal to AC. And for the pair, we write y equal to BCD. So output y will be equal to AB plus AC plus AD plus BCD. And this is the logic circuit for this output y. We have four inputs A, B, C, D. There is no complemented form of these A, B, C, D. So we draw only four lines of A, B, C and D. Otherwise we must draw lines for their complemented form A bar, B bar, C bar and D bar. We will use four AND gates because there are four terms. In one AND gate we have inputs A and B. In other AND gate we have inputs A and C. In one input we must have input A and D, and in one AND gate we must have input B, C, D. And output of these AND gates are made input of this OR gate, and output of this OR gate is y according to this expression. Don't care conditions. Sometimes it does not matter what the output is for a given input word. To indicate this, we use an X in the truth table instead of 0 or 1. These X are called don't cares because they can be treated either as zeros or ones, whichever lead to a simpler circuit. For example, if we consider a truth table like this, these X in output Y represent don't cares, which we can use either as 0 or 1s. We draw Karnaugh map and make quads treating these X as 1s because these are don't cares. We can treat them either 1 or 0. So in the formation of quad, if we use these X as 1s, we can form these 3 quads and a simplified logical expression can be obtained, which is y equal to bd plus c bar d plus cd for these 3 quads. And this is the logic circuit to obtain this output. We have 8 lines, 4 for A, B, C, D and 4 for their complemented form A bar, B bar, C bar and D bar. We will use 3 AND gates and a OR gate. Output of this OR gate Y is equal to BD plus C bar D plus CD, which produces this truth table. In this way, we see how Karnaugh maps are useful in finding a simplified logical expression and to find a simplified logic circuit to produce a given truth table.